So after going to multi-cores, for some years now we see processors with different types of cores. For example, ARM's Big Little as an early example, where some cores are more powerful and also more power hungry, and some are slower and are more energy efficient. We also see cores or CPUs that have additional specialized cores, like crypto cores doing AES encryption or SHA-3 hashing. So they should provide high performance for a very special purpose. We also see all kinds of accelerators that provide computing power for a certain class of operations. And those accelerators appear both on the die and external. The most prominent among them are FPGAs and GPUs. Now, when we see this diversification, it's clear that manufacturers must take a somewhat difficult decision. They must decide what to bring on a die. How many power-hungry CPU cores, how many energy-efficient CPU cores, how many specialized CPU cores. In this slide, flows architectures with some CPU cores and a larger number of PPU cores is not exotic, but it wedges in this scenario as it has different types of cores, and the PPU cores are very efficient both energy-wise and both as they cover a large class of applications. Beyond, this architecture tries to avoid a number of disadvantages that other variants bring. High-performance CPUs normally target a broad range of use cases. So some accelerator or coprocessor should always be there. As PPU cores can replace quite a number of those, it can be a candidate for consolidation in this area. Beyond using only one type of accelerator, if you would name it as such, PPU cores show a simplified programming, because in the end they can be programmed with fibers like we used to program classical multi-core CPU cores, and we don't have exotic programming like in some classic accelerators. So PPU cores show promise to get this field into the next level and make it easier to access for a broad range of applications. Introducing a new type of core is always difficult. So success naturally cannot be guaranteed. However, PPU has at least one advantage. It comes at the right time. So industry must do something, because on the one hand, the requirements for performance go up and up. On the other hand, the operating frequency cannot be scaled up anymore for technology and energy reasons. Also, we cannot simply replicate more and more cores on a large multi-core die, because they simply won't fit on that. So there has to be some way, and PPU shows a promising path where to go without being as exotic as having a very unconventional type of accelerator. So it might now be the right time to introduce PPU into industry and thus raise their attention more than it might have done 10 years ago. I mean, these ideas have been around for quite some time. I mean, it has developed already quite far, and there are patents and there have been prototypes. So it's nothing that has just been invented in the lab last year. On the other hand, 10 years ago, most people say, okay, we have 4 cores or 6 cores or 8 cores on our die, and that's fine. And only for certain scenarios, like more or less embedded systems, energy played the prominent role that nowadays it has for everything. Also, 10 years ago, most processors still were in computers. Today, most processors are not in classic computers anymore, but are in everyday devices like smartphones. So the scenario has changed a lot in those 10 years, but the types of cores that we have did not really. So already ARM speak little, to cite this example again, this looked like a large step, although you just had some faster cores and some smaller cores. They had the same instruction set and they had basically the same capabilities, and that was all. So PPU goes much beyond that, because it's about integrated parallelization, and that is something that I have not seen so far.